Dr. Peter Griffioen now, who's a senior scientist in ecological analysis and synthesis. And Peter provides computer programming skills and undertakes ecological spatial data analysis and satellite image processing. He also curates large in-house ecological datasets, which include extensive flora and fauna records. And today, Pete will be discussing his work on identifying species from their calls using artificial intelligence, which sounds very exciting. And Peter comes to us from Wurundjeri country. Thanks, Peter. I'll hand over to you.
Okay. All right. Well, I am certainly not working in isolation. I'm working with, I'm just going to share my screen here, with Lachlan Francis. Has everyone got that screen? Oops, sorry, gone one beyond.
Yeah, that's great.
We've been working on identifying various species from their acoustic recordings. And there's a large number of projects are starting to use this technology, and they find it very useful for determining communities remotely and analysing their composition, but also for finding endangered species or even feral animals. So the main issue with this acoustic data is that it generates a large number of sound files from the field, which need analysis, and that takes an enormous amount of effort and time. So we decided to step in and try and help improve both the accuracy and efficiency of processing this data. So I'll quickly go over the driving needs of our project to help other scientists, and then I'll quickly describe the model approach that we have taken. Then I'll talk about the data collation and processing. Then we'll have to go through a production environment, because we're not doing this for an academic paper. We're doing this to actually process large amounts of data that are coming in from the field and help the scientists meet their goals. And then I want to quickly go through some new ideas and projects that may stem from this. Now, I'm presenting three different species groups, in effect, in this presentation: frogs, birds, and bats. And all of them are using these remote acoustic recorders in the field. Two of them are related to environmental watering, and they're trying to determine what the effect of the environmental watering up along the Murray-Darling system has on the communities of frogs and bats. And a really interesting project that I've been working on is, Lachlan and I have been working on, is the Eastern Bird bushfire recovery, where they've put out a lot of recorders in the areas that have been hammered by the bushfires in New South Wales and Victoria, and seeing if there's still bristlebirds there and if they're coming back. So they all use automatic sound recorders in the field, and they can, these devices can operate for weeks or even months unattended. So you put them out there, you take a GPS position of where they are, you start them off, and they record onto a SD card, which can be retrieved later. So they can do this. They do this very well, and they set them up for different sampling times for birds, bats, and frogs, and they generate a huge amount of data. So once this data comes back into the office, it has to be analysed to see what species are present. And if we take the frogs for an example, it currently can process about 40 minutes of sound recording every hour to determine what species are there. And that means that you're tying up a scientist for days or weeks listening to this data to determine the communities that are there. And also, because you're using an actual person, there is a fair amount of human variation in that. So, and the effort required and the cost required means that it's possible that you're unlikely to use this data for something else later on. You'd probably go out and get custom data. There are automatic processing options available, but they're generally hard to train and not very accurate. Now, I want you to take special note of that 40 minutes per hour. That means you're processing less than 1 second of sound per second. And why is that an issue? Well, the issue is that we generate a huge amount of files across these various projects. For the frogs, generally you have the recorders coming on for a couple of minutes every, say, 10 minutes late in the day and in the evening. And these will generate lots and lots of files, and we've got over 1 million files, and it's 10 terabytes worth of data. And if you were to listen to all of those files 24 hours a day, every day of the week, it would take you 4 years to listen to them. Similarly, for the bristlebird and other bird projects, which we've only just started really, we've got 17,000 files, but for the bird files, they generally set those up to record for an hour in the morning or so. So they're much bigger files. There's less of them. But again, it would take you a year just to listen to them all. And for the bats, well, the bats have got special recorders that switch on when they hear a high frequency sound from what hopefully is a bat. And so they switch on and switch off rapidly. They generally record very short files in the order of seconds. And there's millions and millions of these, and there's a hell of a lot of data, 14 terabytes. So our brief was to collate these various datas from the field into a database such that it all ends up in the one place. And that way it can be collated and controlled and eventually supplied to a model. We wanted to create a model which would automatically identify the various species within these data sets and do it in an efficient way. We would prefer that the model that we made would ignore a species if it was present rather than get it incorrect. And by what I mean by that is, in scientific terms, we call that we prefer a false negative over a false positive. And you can think of that as, if you're hearing a bird way off in the distance, you could try and guess what that bird is, but you're probably going to get it wrong. It is better to ignore it rather than have the wrong species completely. So wait till the bird gets a little bit closer and then get a good recording of it and then make a guesstimate upon that. The model we're using is a deep learning neural network, and it uses TensorFlow, which is an industry standard deep learning package that runs on PCs and workstations, and it's put out by Google. The type of neural network that we're using is called a one-dimensional convolutional deep neural network, and I have not got time to explain exactly what that is. But let me say, I think a lot of you would be familiar with Shazam on your phone, where you hold up your phone to say what song is currently playing now, and it makes a brief recording, and it goes away, and then it comes back with a pretty good guess of what song is playing. Well, basically, this is that type of technology. So the modeling process is that we need to have examples or exemplars of the various species that we want to detect. And we need to create a database of these. And we've decided for birds and frogs that we'd go for 1.5 second sound samples. And for bats, we've gone for 0.75 seconds. But you don't only need the animals that you want, you also need all the other sounds on the planet, basically, because there are the species that you want and then not those species. So there are lots and lots and lots of different sounds in the world. And if you only present, for instance, a list of frogs, then when it hears a sound, it says, oh, well, what frog is that? Well, you've got to have another option, which is the not on target species or other noises. So there's a fair bit of effort in supplying that. Then once you've got all your exemplars together, you split them up into 2 groups. One is used to train your model, and the other 30% is used as a holdout to test how well your model performs once you have a model. So that way you can scientifically assess, gee, how good it was. And the reason for that is often these models overfit, and so it's very difficult to determine from your training data how well it fits on real world data. A great deal of effort has been put into creating all of these exemplars of the various species, and Lachlan has developed this fantastic software package which can go to the various files collected in the field, and from them create 1.5 second or longer exemplars of the various species. So in this you can see you've got your sound recording file at the top, and in it you can go to a certain spot and find, say, a bristlebird calling, and you can display the songogram there. Then you can listen to it on your headphones. Then you can tag it down the bottom and say, yes, that is an eastern bristlebird. And then it outputs this to the database, which is used later for training. This is an essential part of our software development. Then these data sets, these exemplars are broken up such that they can be used by TensorFlow. And again, I won't go into too much information about this, but basically we use frequency analysis and songograms, if you like, and present to TensorFlow for each 1.5 second 6,900 numbers that describe that 1.5 second of bird or frog sound, or 21,000 numbers that describe that 0.75 seconds of bat sound. And so for the frogs, for instance, we have a model that takes into account 16 species of frog. And then there's the not a frog class, which is every other sound on the planet. Now you might notice there's an interesting frog at the bottom there called frogs galore. I'm sure a lot of you have never heard of that frog. And we found from our model, when we ran it the very first time, that frogs do not like to take turns in having their calls go out. As a matter of fact, they like to call all at the same time. As soon as one arcs up, everyone says, good time to call. And we found that our model couldn't cope with multiple species calling at once. And so we didn't want to miss these events and say nothing is happening. So we came up with a new class that's called Frogs Galore, and it says, okay, there's a lot of frogs calling here. We can't determine exactly what species they are, but there is a fair bit of action happening. And that's so that you still get a continuous level of frog involvement in your file, so that you can, if you like, work out how much activity there is in your frog file. So Frogs Galore is sort of like trying to pick out a person calling out at the MCG when someone kicks a goal. The whole crowd yells, and it's almost impossible to work out what every single person is saying. So every different model has its own sort of quirk like this. For the bat species, again, we've got a multi-species model and not a bat. For the bat exemplars, unlike the frogs and the birds, each one of these bat exemplars is generated from a bat being held in the hand and then released and then recorded. So it's really hard to generate data for the bats to create a decent data set to train the model. For the eastern bristlebird, we've only got a 2-class model because it's an endangered species and we want to find out where they are. And so basically we've got whether the eastern bristlebird is present in a file or not. Once we have assembled all of our exemplars, we stick it all in TensorFlow and let it churn away, generally for only about 20 minutes, and it creates the model. And as I mentioned before, those models are often overfit, and you can see that the training accuracy here is much higher than, or somewhat higher than, the testing accuracy. But the accuracies are extremely high, and we've got very good accuracy numbers to present. Thus, the test accuracy is useful to determine how it may present across the data it hasn't seen. If you look at the 3 different groups that we've done so far, for the frogs, you can see that we've got a lot of exemplars for the frogs, not as many for the bats, and middling amount for the bristlebirds. Now remember, a lot of these are made up of noise, And when you break it into the 30% test exemplars, you can sort of see that the noise is generally much higher than the actual frogs or bats or bristlebirds. Having said that, we are very confident in our results because we've got wonderful results of picking. Remember, we've got sort of 16 species of frogs and we're getting it right 96% of the time. And for the bats, we're getting it correct 87% of the time. Bats are a little bit more difficult. And for the bristled birds, very similar to the frogs, we're getting it correct 96% of the time, basically. What's more, you'll remember that we were only processing files at about 1 second or less than 1 second of recording per second. When we process the files now and pass it through our models, we're getting 400 seconds per second processing speed. Now, what does that mean? It means that, remember, we had 4 years of frog data that you could listen to. Now, on a single PC, we can process all of that data in 4 days. So this is quite significant. And what does the model do? Well, the model outputs probabilities. And here you can see, as the sound file is being processed, the model is making estimates on the 2 main species it hears. This then gets output to a file, which then can be assessed by the scientist to get the species lists and the various abundance measures, if you like, of what species are there. However, sometimes the model doesn't get it right, so you have to validate what the model has come up with. And so to do that, we have another software package called the model validation software, and this is absolutely essential. For instance, we had amongst the frogs again that there was we discovered growling grass frogs in an area we didn't expect. And we thought, wow, there's no growling grass frogs there, we thought. And then when you go to the model validation, this software will bring up the exact file out of the thousands you may have recorded. It will jump to that exact point where the growling grass frog is estimated to be. It will bring up the songogram for you, then allow you to listen to it in your headphones and validate whether that is actually what is there. So this is an essential tool. And in that case, it was a small plane taking off in an aerodrome next to the swamp. And apparently that sounds very similar to a growling grass frog. So these models are iterative in that once you do the validation, you can use this validation software to say, hey, that was not quite right. Here is another noise that is not a frog, and pass that back into the model so that it won't make that mistake again. So where to from here? Well, we'd love to improve our models for each one of those species. We need more data, particularly for some of the frogs and some of the bats. And also we'd like to improve our techniques. Also, it's quite apparent that many other projects can use this technology. And I'm sure there's other scientists out there who are suddenly thinking, oh, wow, if we could process our data through this, that would be wonderful. Well, there's 2 things about it. 1, we need your expertise in identifying the species, and 2, we need your data. So we'd love to collaborate on projects using this technology. We have it at ARI. We're very proud of it, and it works well. We'd love to have more projects in this space. Towards that goal, I'd love to see a bioacoustic library for Victoria eventually. Queensland has such a library. You can see that web address there. Now, a library like that would allow us to reanalyze data in the future if it becomes necessary. For instance, imagine you had sound recordings in areas from before the bushfires, and now you go out and do sound recordings after the bushfires. You could determine the difference in communities before and after the bushfires and say, for instance, find out, did the feral animals come back first or did the native animals come back first? there's all sorts of projects that can stem from this. And finally, let me finish off on the best sound ever that I hear as part of my job. And Louise Durkin is following up with her talk after this. And she said to me, wow, we did not know there were barking marsh frogs at that swamp, and your software detected it. So when there's a discovery like that, that's why I'm doing this. And similarly, from the BirdLife Australia, they put out some recorders in what they said was marginal habitat. And when we reported back to them that we'd found bristlebirds there, they were super excited. And that's what this technology allows you to do. It allows you to perhaps survey a bit wider than you would have before and not worry about the processing. Will help you make the discoveries. So thank you for that, and I'll take your questions.
That's terrific. Thank you so much for that, Peter. It's really exciting technology, and I think we'll really fill in a lot of gaps for us in areas where we may not have a lot of information. To that end, how can citizen scientists help in this space? I know Deborah is very keen to understand how those techniques could be applicable or utilised by citizen science to help this.
Well, there is, ARI is not sort of set up as a software house, so there is that issue, and we can't. But a lot of these projects do involve citizen science in collecting data and also notifying us of areas to, say, put recorders. We can also eventually work towards perhaps some sort of online recognizer, or even one day I dream that I might have a phone app that condenses this software into a phone. So there are various ways that citizen science can contribute. Also with recordings, we can use a variety of recordings. So that's fairly handy as well. Citizen science also can help in the validation of data as well. Terrific.
And I guess one of the other questions Andy's asking about how that frog database system compares to other frog data that's collected, say via Australian Museum or the Frog ID app that they utilise. Is it similar?
Okay, the Frog ID app, I believe, is what they call a mechanical Turk, which is you'll have to Google that. But basically the recording is sent off to a scientist, and then the scientist sends back an email of saying what that recording is. So there is a person behind the screen, which is the idea of mechanical Turk. This is a completely automated system where the WAV file is passed directly through the software, and it makes estimates of all the various species, and it can be a very large list of species. And then if something odd comes up, that is validated by the scientist.
Great. And Cobber is asking, what are the timeframes you estimate for this software to be complete for everyone to use? I think to use, you're thinking more around scientists using, but if your idea of an app came to fruition, what do you think your timeframe for that would be?
Well, ARI is not a software house. We're scientists, and both Lachlan and I are also scientists with sort of software and engineering backgrounds. So we're not set up to sort of develop this as an app per se, but we are initially we look at collaborating on projects, and we can process the data in-house. It is difficult to give the software outside, although we are doing that for the bristlebird, although it does not run as efficiently on outside computers as ours, because we run it on across this technology both uses the CPU and the GPU within a computer. So I'm using a $20,000 workstation to process this, which not everyone has access to. So yes, we would like to get that out there more generally, but it has to be done on a project by project basis at the moment, because that is the way that we are set up. We are not a software house, unfortunately.
Yeah. So Will's just asking, do you work on how to step over from traditional manual monitoring to these digital techniques? So do you provide any training for external organisations or providers?
I have in the past, many years ago, on using GPS receivers, because my original background was in GPS, and then then we moved into satellite work generally from there. But now we're moving back towards this sort of field component. And Lachlan has noted that it is important that people use the right type of recorders and set up the recorders in the right way, such that they are recording information that is the most useful, both for their project and for reusing the data later. For instance, if you set up your recorders at too low a sampling rate, you might not catch the higher frequencies of some of the species, so it might say work for frogs, but it won't work for some birds. The bats are a special case. Those units record super high frequencies, and as a result, their files are very big. So it's very important that people set this up correctly, and we need to perhaps get some of that information out there, because there's a lot of these projects going on, and we found that people have set up their recorders suboptimally in some cases.
Yeah, great. So yeah, that training and understanding would be really useful. That's great, Peter. One last spinner from me is, how does a lyrebird impact your data? You know, given
Yes.
big mimic.
The mimic is going to be a really difficult thing. However, we're making estimates, sort of almost instantaneous estimates. Basically every second we'll estimate what species are there. And as you saw for the bats, our accuracy is a little bit lower for the bats. So sometimes it's making the wrong estimate of what species is there. For the bats, the approach we're going to take is that you take a sequence of calls from the bat, and then you look across that. And when you take the majority of the species estimates, it's correct. So looking across a wider time frame. So I suspect that the same thing would work for a lyrebird. If you're getting a bizarre list of species identifications happening in a sequence, and particularly that they all seem to be at the same volume, then that's probably going to be a lyrebird. So we might have to adjust a model or adjust our post-processing techniques to do strange animals like that.
Yeah, good one. It's always one that's got to make it difficult.
Yes, exactly.
Thank you so much for your time, Peter. I know there's a few more questions, but for the interest of time, we'll have to keep moving, and perhaps you might have a look at those questions and see if you can respond to those in the chat.
Okay.
But thank you very much for your time.